look at what you have there and see if you can. I've actually called your attention to the ones that are incorrect, and I'm going to give you an opportunity to correct them. There's two reasons I'm not going to give the quiz today. That is number one. I want to give you a chance to go back and look at those. And the second one is that we have a lot of stuff to cover today. What we're covering today is, it's frustrating to me that they've crammed all of this into one chapter. That's highly unusual, but we have a lot that we have to do. And it's important stuff, so I don't want to shortchange it. I have some discussions, breakout room discussions for today on the work today, but I'm not sure I'm going to send you to those breakout rooms right away. I think I may send you to those breakout rooms and allow you to work on all of those discussions at once toward the end of class, because I want to make sure that we cover everything. It's just, there's just too much stuff in this chapter, and it's too important for you to not get a chance to do it. So I'm going to, let me just make sure I have this open. Yeah, let's see. We still have some people coming. Okay, let's see, is that's more or less everybody, I think. Okay. Let me go in here and pull up this, and we're not in the right place. So let me go back to the right place. Okay. Okay, so we're going to be talking about a number of models and methods that are used to allow us to talk about molecules, to be able to describe their bonding and the linkage between atoms, and also describe the shapes, because molecules live in three-dimensional space, and we have to be able to talk about them in terms of their shapes, their bond angles, and so forth. So the first model that we use is Lewis symbols. A Lewis symbol consists of the elemental symbol surrounded by dots representing the valence electrons. And you see here some examples of what that looks like. And what we're showing is only the valence electrons. We really are only concerned with valence electrons because it's the valence electrons that enter into bonding. So why do we use Lewis symbols? Well, we can use them to show ionization, and these first two show the loss of an electron for sodium. Sodium would be shown in a Lewis symbol with one dot. We can show its ionization by showing Na plus the electron. For those that are gaining electrons, we have examples here of chlorine and sulfur, where they have actually picked up an electron or picked up two electrons and end up with a full valence shell. We can also show reactions where electrons are transferred. So we can take magnesium and transfer both of its valence electrons to oxygen. I want to point out here that when you do this, note that the oxygen is shown in brackets with the charge outside the brackets. That is the accepted way of showing ions. You have some ions on your lab document that should, if they are a polyatomic ion, once you've drawn the Lewis structure, you should draw brackets around that structure and put the charge on the outside. If you're not, then you're not representing that ion correctly. So that's one of the things that you may want to go back and check before you've submitted that document. The other thing that we can do with Lewis structures is to show how atoms are bonded together in sharing electrons to form molecules. So we have 2 chlorine atoms here, each with 7 electrons. When they form that bond, you have 2 electrons here circled in red, though that is the bonding pair that exists between the electrons, between the atoms, and all of the other electrons, one of which is shown here circled in green, are lone pair electrons. So you have 2 types of electrons in Lewis structures for molecules. You have bonding pairs and you have lone pairs. Now, molecules can also share more than 2 electrons. If they are sharing 2 electrons, that's a single bond. If they're sharing 4 electrons, like the carbon and oxygen down here in our completed Lewis structure, that is a double bond. If they're sharing 3 pairs of electrons, which you have in carbon monoxide, that would be a triple bond. So you're sharing 6 electrons between the 2 atoms. Either of these conventions is correct. You can show bonding pairs as dots, or you can show them as lines. Personally, I prefer the lines. I think it cleans up the structure and it makes it a little bit easier to see. It gets very messy with all of those, I think, with all of those dots around it. If you prefer to draw the dots, that's fine. The one thing I will ask you to do is to make sure your dots are noticeable. If you are, especially if you're using pencil, which I would recommend on a document like that until you know your structure is final and complete, you may have to erase things. You may have to take electrons out or whatever, and it's always better to erase it than to scribble it out. But if you do that, make sure that you actually put a visible dot there. So the question is, how many electrons should you share? All atoms, with a few exceptions, should end up with an octet. The first exception, which is pretty obvious, is hydrogen. It can only hold 2 electrons in that 1s orbital. The other 2 that can have less than an octet are beryllium and boron. Beryllium is satisfied with 4 electrons. Boron is satisfied with 6. So those are exceptions to the octet rule that have less than an octet. In atoms in period 3 or higher, periods 3, 4, etc., can have more than 8 electrons. We call those hypervalent, and we'll see examples of those as we move on. So we've got here structures for carbon tetrachloride, CCl4, silane, which is SiH4, ammonia, water, and hydrogen. These are accepted electron dot or Lewis dot structures. So how did we arrive at those? How do we get them? These are the rules for drawing Lewis structures. The first step you should do is to determine the total number of valence electrons you have available. Your structure will not be correct if it has more or less electrons than the atoms actually bring to the structure. So you total up the valence electrons for each of the atoms in the molecule. You subtract 1 electron for any positive charge that the ion shows, or you add 1 electron for any negative charge that the ion shows if you're drawing structures of ions. The second step is to draw the skeletal structure. A skeletal structure arranges the atoms. The least electronegative element generally is in the center, which, if your formula has been written correctly, in other words, if your atoms have been placed in the formula in the correct order, usually that means that the first atom in the formula is going to be your central atom. So CCl4, carbon will be your central atom. Silane, SiH4, silicon will be your central atom. So generally it's the first atom in the formula. And these will be connected with 1 single bond or a pair of electrons representing the linkage between those atoms. No lone pairs, no double bonds in a skeletal structure. It's just showing how those atoms are linked. So you connect each atom to the central atom with a single bond, and then you distribute all the remaining electrons as lone pairs around the terminal atoms. So you look at the number of electrons you should have in your structure and subtract from that all of the electrons that were used in the bonds in the skeletal structure. What's left are the electrons that need to be distributed around those terminal atoms. And you do that so that each atom has an octet. If there are any more electrons remaining after that, they are placed on the central atom. The final thing that you should do is check to make sure everybody has an octet and then count your electrons. I can't emphasize that enough. You can create all kinds of structures that look legitimate, but if it doesn't have the right number of electrons, if it has more electrons than what you started with, or fewer electrons than what you started with, the structure can't be right. So you have to count the number of electrons that you have in the structure and then rearrange those electrons as necessary using multiple bonds with the central atom in order to obtain octets and the right number of electrons. So that will help you address any electron shortage. So we're going to do some practice here. We have already seen what this looks like, but this structure has 4 electrons from carbon, and it has 28 electrons from the 4 chlorines, so you should have 32 electrons in your final structure. Carbon is the central atom. My skeleton shows 4 bonds to 4 chlorines. Next step is to draw lone pairs around each of my terminal atoms. And then the last step is to count electrons: 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So my structure has 32 electrons. Everybody has an octet, so the structure is finished. When I do CH2O, I have 4 electrons for carbon. I have 2 electrons, 1 from each of the hydrogens, and 6 electrons from oxygen. So I have 12 electrons that I can put in my final structure. So my first step is carbon in the center. Single bonds, whoops, I'm sorry, that's incorrect. That should be a hydrogen. Single bonds to each of my connecting atoms, and then I'm going to put remaining electrons around. Now I'm going to count them. I use 6 in the bonds, and I have 6 over here. That's fine. That's the correct number of electrons: 2, 4, 6, 8, 10, 12. But if I notice, carbon has no octet. So this structure cannot be right. And in order to fix this structure, I'm going to have to remove one pair of electrons from, why does it not want to do that? I want to erase that. Come on. And I'm going to have to put in an extra bond. You know what I think my problem is that I need to go. I'm sorry. I'm going to reshare this in a different way. Slideshow. Okay, this way it will work. So I'm going to erase this. Whoops, that's not right. I'm going to erase this. Oh, it's not going to do it now. and I'm going to put a second bond in here. So I have a double bond here. I'm going to have to cross these out. Now you see the problem with not being able to erase. Now when I count, I have 2, 4, 6, 8, 10, 12. I have 12 electrons, and now my carbon has an octet, so that problem has disappeared. So let's do one more. I have NO. I have 5 electrons from nitrogen, and I have 6 electrons from oxygen, and I'm going to subtract 1 for the charge. So my structure should have 10 electrons. So I'm going to put N and O together. I've used 2. That means I have 8 electrons that I can put around. But if I put my octets around both atoms, you'll see that I have 2, 4, 6, 8, 10, 12. I have 14 electrons, which is too many. So now I have too many electrons in my structure, and I'm going to have to add double bonds to fix that. And the way you do that is if you take 2 electrons out from 2 neighboring atoms, I've now removed 4 electrons, and I get a pen back, put a double bond in. So I've removed 4 and added back 2. So if I have 2, 4, 6, 8, 10, 12, that's still too many electrons. So I'm going to have to do the same thing again. If I go back here and take my eraser, I erase 4 electrons and I put back 2. So I take out 4 and I put back 2. Now I have 2, 4, 6, 8, 10 electrons, and that is correct. So that's really how we get these structures.
Question.
Professor?
Sorry, can you go back to the previous slide?
Sure.
So with oxygen, if we write it as a single bond of oxygen on each side, would that, oh, never mind.
You mean, wait a minute, would this one, this NO plus?
I was talking about CH2O.
This one, yes. If you write it as
a single bond, I was going to ask if you write it as a single bond on each side, would that be incorrect? But never mind, because it has to have 4 electrons on it, right?
yes.
Okay, thank you.
Yes. So these are some more examples of the same kind of thing. I'm not going to do these with you now because we have so much to do today that I'm going to let you use this PowerPoint and do your own practice on these. Remember, count the electrons first and then draw your structure. You actually have examples here of both types of problems where once you've finished, you either don't have an octet on one of the atoms or you have too many electrons. So let's talk a little bit about some of the oddities. As I said, there were 2 atoms that allow deficiencies in electrons, beryllium and boron. And BeH2, this is one example of, this is a perfectly normal structure. And boron trifluoride has 3 fluorines around it, and there aren't enough electrons. If you look at this structure, the first question I think a lot of students ask is, why don't we just take out one of these pairs of electrons from fluorine and just stick it in here as a double bond? The obvious question there is to say, fluorine is the most electronegative element on the periodic table. How likely is it that it's just going to voluntarily away to another atom like boron, which is not nearly as electronegative? So that's just not the way it is formed. It's perfectly happy with these 3 pairs around it. That doesn't mean that it's not reactive, though. They are very reactive molecules, and because the boron is electron deficient, without an octet. So when it comes in the neighborhood of a molecule like ammonia that has a lone pair of electrons, that electron density can actually form bonds with the boron. This is actually called a Lewis acid-base reaction. And so you form a bond between the nitrogen and the boron. So this is a fairly, this reaction happens fairly readily because boron is electron deficient. It can stay with 3 bonds, but it's not as happy as it would be if it had an octet. Also, you can see some rather strange bonding where you get 2 electrons bonding 3 atoms, like we've drawn down here before, and we draw that with dotted lines. So they're very reactive molecules, but these, as shown above, are the correct Lewis dot structures for those 2 atoms. The second oddity is the hypervalent atoms. These are atoms that can have more than 8 electrons around them. This happens in period 3 or higher because at period 3, you start having d orbitals. Remember that in period 2, you have only the 2s and the 2p. But once you get to period 3, you have 3s and 3p and 3d, and those 3d orbitals are empty. So you can actually incorporate some of those d orbitals for holding electrons. So there's a couple of ways that you get that. One of them is if you have molecules where the central atom has to be bonded to more than 4 atoms. PCl5 and SF6 are 2 perfect examples of that. You have to have extra pairs of electrons bonded to that central atom in order to do that. The other way hypervalence is from leftover electrons in your Lewis dot structure. So we have 2 examples here, iodine pentafluoride. Once we count the electrons and put them in and put all the lone pairs around the fluorines, we still have 2 electrons left over. They have to go somewhere, so they go on that central atom, even though that means 6 pairs of electrons surrounding the central iodine. The same is true for xenon tetrafluoride. Once you've put octets around all your terminal atoms, you still have 2 pairs of electrons that you have to place. And so they go on the central atom. So your central atom xenon here has 6 pairs of electrons around it, 2 as lone pairs and 4 as bonding pairs. So those are the 2 ways that you get hypervalence. Now, some of you may be looking at molecules like this if you've been paying attention and said, wait a minute, xenon, that's a noble gas. I thought noble gases didn't form bonds, they didn't form molecules. In fact, they generally don't, but the larger ones, particularly krypton and xenon, because they are going into orbitals that are pretty far away from the nucleus, they actually can form bonds, but only with something that is highly electronegative, i.e. with fluorine. So you will see krypton and xenon molecules involving fluorine, and that's what we have here. The final oddity that we want to talk about is the radicals. These have an odd count of electrons. Generally, in first-year chemistry, most of the things that we give you will have even numbers of electrons. So we ask you to draw a Lewis dot structure for nitrate, NO3 minus, but not for NO3, because NO3 is electron deficient. It has an odd number of electrons. When writing the Lewis dot structure, you would have to put make the more electropositive element the one that's electron deficient. So we have NO here. This has 11 electrons, 2, 4, 6, 8, 10, 11. And so we have this 1 electron by itself on nitrogen. Nitrogen is less electronegative than oxygen, so oxygen is more likely to have the full octet. Same thing is is true with the molecule below. You have one extra electron. These are called radicals, and they're highly reactive. They when two of these molecules, NO molecules, come in proximity to each other, they're going to combine. Two of them will combine very quickly to N2 O2. They won't, they're not happy. They're not happy, and they will scavenge electrons wherever they can. And these are the kinds of reactions that are responsible for things like the destruction of the ozone layer and things like that. Those are radicals. In that case, you have chlorine containing compounds, or let's say we had a Cl2 molecule and we broke that up into two Cl atoms. Now they are radicals because they have an odd electron. And these species, it's this species that is looking to scavenge electrons from somewhere, and that's going to attack ozone to try to satisfy its octet. And that's where you get the destruction of the ozone layer. So radicals are highly reactive, and we generally don't ask you to draw those Lewis dot structures. So we have to talk about formal charges, because sometimes there's more than one way to draw a molecule, and we might want to know which way is better, which way makes more sense, which way is more stable, which is the better structure. So we talk about a concept of formal charge. Formal charges are not real. They are not real. They are not real charges. They are simply our way of accounting for electrons in the molecule. And assigning those electrons in a way that we can identify how much electron density is around each atom. So the way we do that is we take the number of valence electrons that the free atom had. How many valence electrons did it have as an element? And we subtract from that the number of lone pair electrons that it has in the structure, and 1/2 of each bonding pair of electrons to determine what the formal charge on that atom is. So let's take a look with a couple of different examples. Down here we have 3 possible ways of drawing carbon dioxide. Notice that we've actually had to come up with 2 different bond orders. We have carbon in the center with 2 oxygens on either side, or we have oxygen bonded to carbon. That's a slightly different way, but let's look at them and assign formal charge. We'll start with the carbon here. Carbon brought 4 electrons with it. It has no lone pairs, but we take 1/2 of each bonding pair. So 1/2 of each of those 4 dashes. So it's 4 minus 4. So it has a formal charge of 0. Oxygen brought 6 electrons. We have to subtract from that each lone pair. So we subtract 2, 4, and 1/2 of each bonding pair. So 1/2 of each of those dashes. So it's 6 minus 6. So it has a formal charge of 0. And the same thing for this oxygen. So now we've got another alternative structure where we have a triple bond on one side and a single bond on the other. Carbon still has 1/2 of each bonding pair, so it's 4 minus 4, so it still has a charge of 0. This oxygen over here came with 6. We subtract from that the lone pair and 1/2 of each bonding pair, which is 5. So this has a formal charge of +1. It's got 1 fewer electron than it came with. In this case, we have it came with 6, we subtract half the bonding pair plus the 6 electrons in this side of the molecule has a -1 formal charge. So we're subtracting more electrons than it came with. This final one, we have oxygen in the center. It came with 6. It's got half of each bonding pair, so this is going to have a charge of +2. The oxygen on this end came with 6. We're going to subtract 4 and half of each bonding pair, so it has a formal charge of 0. And the carbon came with 4, and from that we're going to subtract half of each bonding pair. That's 2 plus 4, so this has a -2 formal charge. Does everybody understand how to do that now?
Can you do the last one again? I'm sorry.
This one, the OOC?
Yeah.
Okay, oxygen came with 6. We subtract half of each bonding pair, so we're subtracting 4, so 6 minus 4 is 2. On this side, we have oxygen that came with 6. We're subtracting both lone pairs, that's 4, and half of each bonding pair is 2, so 6 minus 6 is 0. And for the carbon on the other end, it came with 4 electrons. We're subtracting 4 electrons for the lone pairs, and half of each bonding pair is another 2, so it's 4 minus 6 is -2.
Okay, makes sense.
Okay, so we can look at these, and let me just check the second slide.
Professor?
Yeah, it doesn't say, yes.
And those are in order of stability, right? Like the first one's the most stable?
Yes, I was just checking the next slide to see if I talked about it on a separate slide, and I did not. So how do we know what makes the most sense? There are basically 2 rules on what makes a structure stable, or let's say what makes a structure more reasonable. This structure is very different because you have a different bonding order for the atoms. But the first 2 are essentially the same molecule. It's just where those bonding pairs are. And so this one we can look at and say, well, this has got a large charge separation. So that doesn't make a whole lot of sense that is the way that it would be bonded. But when we look at the first 2, they're bonded in the same, the atoms are in the same order. It's just the bonds that have shifted. What makes a structure the most stable is the least amount of formal charge. Let's put a formal charge. The least amount of formal charge is what's going to make the structure most stable. We're going to do this next one, and I'm going to point out to you that these are ions and they have an overall negative charge. So in this case, I'm going to have to end up with a formal charge. There is going to be a formal charge in the molecule. But for a neutral molecule, if you can describe a structure that has 0 formal charge on all of the atoms, that makes the most sense. If you have a charge, if you can't create a structure that doesn't have some charge separation, the least amount of charge separation that you can get is the best. And the second thing is that the atom that has a negative charge on it, a negative formal charge, should be the most electronegative element in the structure. So let's take a look at this second one. Again, we have carbon brought 4, has half of each bonding pair, so it has a formal charge of 0. Nitrogen brings 5. Whoops, sorry. Nitrogen brings 5, and in this case, we have to subtract 6, 2 for each lone pair, half of each bonding pair. So it's 5 minus 6, excuse me, for a -1 formal charge. And sulfur came with 6, and we're subtracting 2, 4, and half of each bonding pair. So this has a formal charge of 0 as well. We have different bonding. Each of these represents a different bonding order. So let's talk about nitrogen in the center. Came with 5, -4, has a charge of +1. Carbon came with 4. We're subtracting 6, so it has a charge of -1. And sulfur came with 6, and that's something can't be right here. 2, 4, 6. I'm sorry, this is a -2. 4 minus 6 is 2. And sulfur came with 6, and we're subtracting 6, so it has a charge of 0. Now, you might ask how I knew that I made a mistake. The overall charge on the ion is a -1, so I have to have an overall -1 somewhere in my entire structure, and my first structure has that. If this was -1 and +1, and this was 0, that would end up with no formal charge, and that doesn't match the charge on the ion. That's how I knew I made a mistake. Okay, so the last one, sulfur came with 6, -4 is a 2, a +2. Nitrogen came with 5, -2, 4, 6 is a -1. And carbon came with 4, and we're subtracting from that 2, 4, 6. So this is a -2. So we can say right off the bat that there's a huge amount of charge separation in this last one. That structure doesn't make sense at all. And if we look at these other two, we can see that the first one makes a lot more sense because it has the negative charge on the most electronegative element. That's not true in the second one. The charge is on the carbon. And the overall charge is as low as it can possibly be. It has to be -1 somewhere, and that's one atom has a -1 charge and the other two are both 0. So that makes the most sense. So when you have more than one possible way of arranging atoms or arranging the double bonds between the atoms, you can use formal charge for figuring out which is the best way to do it. Which brings us to resonance forms. It turns out that there are some molecules have several possible valid Lewis dot structures, and we call them resonance forms. So we have an example here of the nitrite ion where we have both of these molecules show the right number of electrons. They have the negative charge. If you looked at formal charge, it would be on one of the oxygens in both cases. So both of these are reasonable structures. And I've had students ask me before, what is the difference between this first structure and the second structure? It looks like I've just flipped it. And maybe the molecule is just turning over. We're going to learn that the strength of the bond between atoms is different for a single bond and a double bond. So an NO double bond, like we have here, is a stronger bond than an NO single bond. The bond length is also different. The more electrons that are shared between two atoms, the closer those atoms are held together and the shorter the bond. So when you look at these Lewis structures, the suggestion is that you have two different bond lengths and two different bond strengths. And the fact is you don't. The bond length and the bond strength is identical on both sides of the molecule. So that means that neither one of these structures is correct. And the way I like to describe it is to say that the molecule is really a hybrid between the two. If you think about a mule, for example, a mule is a cross between a horse and a donkey. A mule doesn't look like a donkey one day and look like a horse the next. it looks like a mule. It looks like a mule all the time. So it is a hybrid between the two. And the actual structure for nitrite is a hybrid between these two. This is a failing of the Lewis dot structure system. If I have to invoke a concept like resonance, I'm invoking it because while these are both correct Lewis structures, neither one of them actually represents what this molecule looks like. The molecule looks like a blend of the two, an average of those two. These are two legitimate structures and their formal charges are going to be identical. The question is, what happens if they are not? If we looked at this last one, for example, these are two resonance structures that are not identical. So what makes it stable? We said before, either no formal charge if it's a neutral molecule, or as few formal charges as possible. Formal charge as close to 0 as possible. So 1 is better than 2, 0 is better than 1. The negative formal charge has to be on the most electronegative element, and any positive formal charge should be on the more electropositive element. So the actual Lewis structure for nitrite would be better represented by this structure, where this dotted line represents that extra electron pair being shared between all three atoms. So that what you really have is not a single bond and a double bond, but really kind of 1.5 bonds between the nitrogen and each of the oxygens. So that represents a better resonance structure. Now there is a breakout room practice. I'm going to wait till the end and give you a chance to go back and look at that. Because we still have a lot to do today. And the first is looking at molecular structure in 3-dimensional space. One of the failings also of Lewis structures is that these molecules are shown in 2-dimensional space. Notice that I've actually drawn it bent down here, where they're drawn linear up above. The one on the bottom represents the actual shape of this molecule better than the one up above. And many of you who've taken chemistry before will notice that science teachers, chemistry teachers have a tendency to draw bent molecules as bent molecules. We don't like to draw them as linear when they're not linear, because they don't represent what the molecule actually looks like in 3-dimensional space. So there are certain things that come into play when we're talking about 3-dimensional space. One is the bond length, and that's measured from the center of one atom to the center of the next. That's the bond length, center to center. And they are on the order of 10 to the minus 10th meters, or that's angstroms. The other thing is the bond angle. What is the angle that exists between those two atoms? So the things that impact the shape of the molecule will be the electrons surrounding that atom. Electrons tend to, because they're negatively charged, electron pairs will tend to repel each other. Like charges tend to repel each other. So dense regions are going to try to get as far away from each other as they possibly can. They're going to orient themselves in space to be as far apart as possible. And this is called, we call it VSEPR, valence shell electron pair repulsion. And this is the theory that governs the shape of molecules. Valence shell electron pair repulsion theory, or VSEPR theory. It allows us to predict molecular shapes in 3 dimensions from a Lewis dot structure. So we can draw them with Lewis dot structures, but the shapes that we draw are going to be generally in 2-dimensional space, and they're going to look like they're all 90-degree bond angles, but they're not. The trick to this is always put electron regions, whether they're bonding pairs or lone pairs, as far away from each other as possible. So each molecule can be described in two ways. We can describe the electron pair geometry, and we can describe the molecular geometry. These are different because electron pairs represent the number of electron regions, but when you look at the molecule, when you actually look at the molecular shape, lone pairs are, it's like they're not visible. And I like to liken it to taking an X-ray. When you take an X-ray, you see the bones, you don't really see soft tissue. So when you look at ammonia down here, we have this lone pair up here. This is just electron density. The real density of the molecule occurs in the nuclear centers. So if I were to liken this to taking an X-ray, the dense part of it is really the nuclei. And so the molecular geometry is determined by this bonding structure. The electron density influences the structure, but it's not part of the molecular structure. It's a part of the electron pair geometry, but not part of the molecular geometry. So when I look at the molecule, this is what I see, is this shape down here. I really don't see those lone pairs up there. Those lone pairs influence the geometry because they are going to repel the other electrons. So they're there and they influence the shape of the molecule, but they are not counted as part of the molecule, and they will affect the bond angles. So these
Can
are
I-
the, yes.
Can I, yeah, sorry, I just need to take it back for like 5 steps really quick.
Sure.
For resonance, I'm still trying to comprehend, was there like, is it essentially any sort of different structure of that molecule that can be considered resonance, or is there some sort of like,
Generally, to be a true resonance form, the only thing that changes is where the electrons are. The bonding sequence of the atoms doesn't change. Notice I have O, N, O in both of these. I don't have NOO or OON. So to be a true resonance form, the atoms have to be linked in the same order. What changes is the position of a double or a triple bond.
right?
That's the
Okay.
only thing that changes. Okay.
Okay. I got it.
When I did this bottom one, these are not true resonance forms. What these are down here are 3 alternate ways of thinking. If we have NCS, how would we know which order to bond those atoms together? Can we predict which is the best bond, which is the best sequence for those atoms? And it turns out we can. NCS is a better sequence than CNS or CSN because of formal charge. So these are not true resonance forms. They're just alternate bonding patterns, and we can use formal charge to identify which is the better one.
Okay.
These are true resonance forms because the atoms are linked in the correct order or the same order. The only thing that has changed is the pattern of electrons linking them. It's really movement of double or triple bonds. Okay. All right. So these are the fundamental shapes, and we'll talk about distortion of those shapes in a bit. When you have 2 atoms linked together, or you have 2 regions of electron density, it's linear. It's as simple as that. Excuse me, 1 region. This is 2 atoms bonded together. You really have 1 region of electron density linking those 2. If you have two regions of electron density here, this would be, one example of this would be CO2, which we drew before. By the way, when we're talking about the shapes, we're actually talking about the shape around the central atom. So we're really focusing on this guy right here. So CO2 is one. Another one was that, remember we had BeH2. If this is Be and we have an H on either side, we have a single bond between the two. Those are two regions of electron density. And the farthest apart those two regions can get is 180 degrees. Okay, it's very simple. This molecule still, by the way, is in two-dimensional space. It's not, it hasn't had to occupy three-dimensional space yet. Trigonal planar, this would be where there is a central atom that has three regions of electron density surrounding it. And we can talk about some examples. One example of that we did already, BF3. That was a perfect example of this. NO3 minus would be no, let's see, NO3 minus I think is an example of this. But with three regions of electron density, the farthest they can get apart from each other is 120 degrees. And that is still also just flat. It's in two-dimensional space. So now we have a new name for that. We're going to call that trigonal planar. It's in one plane, so it's called a planar, and the trigonal means that it's shaped. It's got that triangular shape. When we get to four regions of electron density around our central atom, remember we're focusing on the central atom, now suddenly we have to go into three-dimensional space to get those as far apart as possible. One example of this would be CH4. And if we were to draw CH4 with a Lewis-Strauss structure, it's going to look like this. That looks like we have 90-degree bond angles, but that's because the Lewis structure is drawn in two-dimensional space. That's not as far apart as those electron domains can get. If we start occupying three-dimensional space, we can actually create a structure where this angle is 109.5. And that allows those electrons to get as far apart as possible. The name of this shape is tetrahedral. If you have five regions of space, an example of this we saw as a hypervalent, PCl5 is an example of that. Five regions of space, there's our central atom, that would be phosphorus, and each of these would represent a bond to a chlorine. This is the only shape that has two unequal bond angles. We have two types of electron domains here. The one going straight up and straight down, we call those axial electron domains, and the ones going out this way, those are called equatorial. The equatorial domains are much like our trigonal planar. Those are 120 degrees apart. So the bond angle here is 120 degrees. But to go from the axial to the equatorial, those are 90 degrees. So this is the only shape that actually has two unequal bond angles. And that's going to be important when we start looking at where the lone pairs might be in certain molecules. This is called a trigonal bipyramid. If you think of a pyramid having a square base and pointing up to an apex, this is very similar to that, except the base, instead of being square, is actually triangular. So you have a trigonal bipyramid because you have an apex pointing up and an apex pointing down. So it's a trigonal bipyramid. And the last one is when you have six regions. We had an example of this as SF6. And in this case, we now have all the same angle again, because both from the axial to the equatorial, this is 90 degrees. And also from the equatorial, we now have 4 equatorial electron domains, and they are also 90 degrees apart. And this is an octahedron. If you think of the plane that is formed between these 3 atoms, that plane is repeated 4 times around the top and 4 times around the bottom. So it actually has 8 triangular planes on this molecule, and therefore it is called octahedral. So those are the basic shapes that you would get based on the number of electron domains surrounding the atom. These are if all of those electron domains are bonding electron domains. Where you get distortion is when you have lone pairs instead of a bonding pair. And that comes because lone pairs tend to spread out in space a little bit more. If you think of these electrons here between these 2 atoms, they're sort of, those electrons are anchored between the nucleus of the central atom and the nucleus of the bonded atom. So those electron pairs tend to be anchored in space a little bit on both ends, whereas a lone pair is only anchored on one side. And so they tend to try to spread out in space a little bit more. And in doing so, they're going to repel the bonding pairs around them a little bit more. So lone pairs tend to repel more, and they will tend to spread out a little bit. Double bonds, if you have double bonds, you're sharing 4 pairs of electrons. Those also want to spread out a little bit because you have 4 pairs of electrons being shared between 2 atoms. So you get a little bit more repulsion. Lone pair electrons, if you have 2 lone pairs on the same atom, they tend to repel each other most. That repels more than lone pair bonding pair, and that repels more than bonding pair. You also have lone pairs will repel greater than triple bonds, which will repel greater than double bonds, which repel greater than single bonds. So you have varying repulsion between neighboring electron domains depending upon what character those electron domains are. And so you end up with all kinds of shape changes. We're going to have to talk about the shape of the molecule, and the shape of the molecule, the shape of the electron domain will always be the same. If you have 2 electron domains, it's linear, 3, it's trigonal planar, 4 electron domains, it's tetrahedral, 5, it's trigonal bipyramid, and 6, it's octahedral. But when you start replacing those with lone pairs, the shape of the molecule will change. So if we have 3 electron domains, but one of those is a lone pair, the shape of the molecule is determined by this part of the molecule, the AX bond angle. And this is called bent or angular. This lone pair can try to stretch out a little bit. So the bond angle, which is normally 120 degrees, will be slightly less than 120 degrees here. But the molecule, the molecular shape is bent or angular. For the tetrahedral molecule, the bond angle is 109. If one of those is a lone pair, example here would be NH3. This lone pair is going to try to spread out a little bit. It's going to press down a little bit on this bond angle, and you're going to have a bond angle of somewhat less than 109 degrees. It's generally about 107 degrees. The shape of the molecule is determined by this part of it. It's a triangle, but it's not flat. It's got a little bit of a lift to it. So it's called a trigonal pyramid. If you have 2 lone pairs, an example here would be H2O. You have 2 lone pairs on your oxygen, and they are both going to want to spread out in space. So the shape of the molecule here is bent. That's why chemists tend to write the structure of water like this as a bent molecule, even if they don't bother putting in the lone pairs, which would be up here, but even if they don't put them in, they will write water as a bent molecule. And the bond angle is going to be much more compressed than it is with only one lone pair. You can simply say much less than 109.5. Oh, excuse me, 109. It's actually about 104.5 in water. If it's different constituent atoms, it might be a little bit different, but it's less than 109 because those two lone pairs will spread out a little bit more. So each of these has a name. The name here represents the molecular structure. When we get down here to